subatomic particles. For sure, we've got covered with our mass number, our protons and neutrons. Our atomic number gives us our protons. The upper right-hand corner gives us information about the charge. And our charge is our protons and electrons. Officially, though, it's the charge from our protons plus the charge from our electrons, which is why they cancel out, because electrons are negative and protons are positive. Yeah? When we're looking at atomic notation, one of the things that the textbook and I think a lot of people will go through and use to say, well, we don't need to address that, is that typically the charge, at least at this stage in the game, is what?
Neutral.
Neutral, which means we're not going to write anything in the upper right-hand corner because there is no charge, so we would just write 0. Okay? What that's meaning is we have the same number of protons as we have electrons. We should be more explicit in stating it. The lower right-hand corner is where we would specify the quantity, okay, of our element. So when we,
quantity of element.
what's written in the lower right-hand corner,
The number of molecules that you're looking at.
in this case it's not molecule, this is H2O, this is one molecule. So our lower right-hand corner isn't in reference to molecules, it's in reference to the number of atoms or element that's present. So when I look at H2O, what's written in the lower right-hand corner of H2? Which means there are 2 hydrogens in water. Right? How many oxygens are there in water?
One.
This case, an implied or nothing doesn't mean 0 in this case, it means 1. So that blank has different meanings in different situations. If it meant 0, then this formula becomes a bit of a pain, because what else would we have to do? Carbon, nitrogen, helium, lithium, beryllium. We have to specify every single atom because the implied right-hand corner was 0, not 1. Okay? So the implication changes, but it's a lot of it has to do with the context of what makes that easier to manipulate and use. Kind of make sense? If I want to specify the number of the molecule that is present, that becomes trickier. Where would I place information about how many water molecules there are?
To the left of the H.
To the left of the H. And I'm not going to go as a subscript, because if I want to have as a subscript, what would that look like? That would be atomic number. So I can't use a subscript or a superscript. I end up using just a normal font, okay, out front. So the number of molecules is a number way out to the left. Okay? The number of atoms in a molecule is going to be a subscript, charge, superscript, right, all that fun stuff. Kind of make sense? It's kind of our basic structural placement of where that information goes. So if we were going to use the atomic notation that is shown above, we could go through and answer some questions about it. So first off, we should be able to identify that the element is, how do we know it's silicon?
Periodic table.
Right, periodic table, where does it say silicon on the periodic table?
Front page of the book.
On the periodic table that we have for our exams.
It does.
It doesn't. So how would we know SI meant silicon? You'd have to memorize it. It's one of those elements that you're going to need to memorize. Okay?
Wait, which ones were the ones that we have to memorize? The ones on
So there's that file on Canvas that is elements for memory. Everything on that page you should memorize.
but the ones.
Everything of critical importance to memorize is bolded.
Oh, okay.
Right?
But I have to memorize all of them.
You should memorize all of them.
Okay.
Yeah. Okay. So because we've memorized something about the language, we know our symbol, and now it's going to delete all that work. Okay, or our compound is silicon. We have an atomic number of 14. So what does that mean? 14 protons. What else does the information of 14 as an atomic number tell us?
It's 14 electrons.
Atomic number of 14 doesn't mean 14 electrons. If the charge was 14 or 0, then I know I have 14 electrons. We haven't, if we're only looking at the atomic number, I have no idea what's in the upper right-hand corner. Okay? So this is a bit tricky because it's actually redundant.
I don't think I have it, but the number of neutrons?
Nope. okay? Because our atomic number is just the number of protons. The number of neutrons has to do with our mass number, okay? So like I said, it's redundant information, okay? Our number of protons is 14, that's true. What is the redundant piece of information when I tell you 14 protons?
No, never mind, I was gonna say something there. The number of
Silicon.
atoms, or the number of atoms.
No, it's not the number of atoms.
Silicon is 14 protons.
It's that it's silicon. If we just know the atomic number is 14, we can use the periodic table, right, and it tells us SI. So the redundant piece of information coming from the atomic number is what the element is. If we had the element symbol, we also knew that. Does that make sense? That's why the information is redundant. We're seeing it in two places. Right? We're effectively seeing it as a alphabetic code with the SI, and now we're seeing it as a numeric code, 14, which translates to an SI. Yes?
So, you know, like how the numbers, like, it's not like a whole number, would you round like that?
What's not a whole number?
Like the mass number, would you
Right.
round or would you?
The mass number is not a whole number. That is actually a false statement. The mass number is always a whole number. Keep trying.
Like, so, if I had to do,
Pick one.
for example, like, I don't know, neon, and it's 20.18 and then 10, so would it be like 10.18?
Okay, so let's pause for a second here. So, and I've got it up on the screen so we can see it too. So this is what our periodic table looks like. What is the 10? The atomic number. Where's the atomic number supposed to be written? In our notation in the bottom left. Is it written in the bottom left?
No.
No. Okay, so why is it changed?
Because it's not, for, you said that was for nuclear stuff, so it's
The
more.
context of who we're presenting that information for has changed, okay? So that's one of the big things that we've got to be careful of. The periodic table organization is based off of all chemists. Nuclear notation is largely for nuclear chemists, and so the placement of that information changes around a little bit, okay? So in our upper right-hand corner on the periodic table, and that will oftentimes slide around. Some periodic tables will put it right in the middle, which I think makes a little bit more sense because then it's not overlapping any of our other locations, okay, would be our atomic number, okay? To where you were getting at wasn't asking about the 10, you were asking about
The neutrons and the.
the 20.18, okay? Well, the mass number is the protons and neutrons, okay? At this stage in the game, and as far as the semester goes, those are our smallest subatomic particles. It's not true, but that's where we're working. Right? So I can't get smaller than one proton. I can't get smaller than one neutron. Does this make sense as a mass number?
No.
No, because I have 0.18. That means I have fractional protons and neutrons. That doesn't make sense. You could say, well, that's the number of electrons. If it was neutral, it has 10 electrons. 10 divided by 1,816, whatever that number was, does not equal 0.18. Okay? So what is that 0.18? Okay? Said an entirely different way, you are assuming that 20.18 is the mass number. Is that what our periodic table says is written there? That is the atomic weight. Is that the mass number? No. They are entirely different things. Sort of. Okay? They are entirely different things, but tied to each other. They're related, but they're different. Okay? So when we look to the periodic table, the mass number is not there. Okay? The mass number would be given to you in a question. Okay? I'm looking at copper 65. The mass number is 65 for that copper. Okay? I'm looking at neon 20. The mass number is 20. I'm looking at neon 21. The mass number is 21. Okay? The atomic weight, which is better called the atomic mass, is not the mass number. And we'll see that in a little bit. Okay? Or we'll specifically address that in lecture. Does that cover you for the moment?
Yeah, I was just
Yeah, it is easy to confuse. And that language is so confusing that for whatever reason, we've decided to put that in an exam question.
You
So-
put it in an exam question for us.
I did not put it in an exam question because I think it's exceedingly confusing. But we did. Mass number, atomic mass are two different concepts, and you got to keep them separated. Okay? Which I think was just a sidetrack or just a tangent, right? We don't have any questions about what's up on the board right now, at the moment? Okay. So, with a mass number of 29, what do we know?
Has 15 neutrons.
It has 15 neutrons. How did you get 15 neutrons?
Subtracted 14 from 29.
Okay. What that 29 means is that we have 29 protons and neutrons. Okay? This is an equality. Since I know the number of protons is 14, I can now solve for the number of neutrons through a little bit of math. And as Rose just showed us, she's really good at math, and she could do that all either in her head or she wrote it out already. And we get 15 neutrons. Make sense? Okay. So those are the kind of things that you could expect to do when looking at atomic notation. Those kind of questions. We good? Okay. So, before we push into what we're going to look at here in a second, our atomic mass. Did I hear?
That's the
Oh, wait.
solution. Sorry, for the number of.
Yeah, what just advanced out was the solution. Yeah. Okay. This table is very, very similar to what I already told you to memorize. The one thing that's different is I've added an extra column on it saying the meaning. You should be able to go through and fill in for each and every single one of those all of that information, like the location of an electron. Okay, outside. Outside what? Outside nucleus. Protons. Inside nuke, right? Mass.
0.
0, assuming electrons. 1, 1. Charge.
Negative.
-1, +1,
0.
0. Make sense? Symbol?
A minus.
E minus, P plus, and then 0. Yeah? It's supposed to be a 0. Hey, it looks better up there. What is the meaning? Right? The meaning is a lot trickier. Okay, so what we're going to do is think about this a little bit differently because it's organized in a way that probably isn't ideal. I would argue that we should start the meaning question by looking at the protons. Okay? I give you 6 protons. What can you tell me? I have 6 positive charges. True. What else could you tell me?
What other ones have 6 negative charges?
If I just tell you 6 protons, do you know how many electrons are there? No, which means you don't know the charge either.
It's carbon,
How do you know it's carbon?
because the atomic number identifies the element.
6 protons is carbon. Right? You're like, why? That's an interesting. Why would I put 6 up there? That's exactly why I picked carbon up there, and that's why I picked that. So the number of protons tells us what? What's the meaning of the number of protons?
The element.
It defines the element. Once I have now defined the element of carbon, right, and I now say 6 electrons, what does that tell me?
The charge code is here.
That defines the charge. Yeah? What if I now tell you you have carbon and 6 neutrons?
That defines mass.
Now I've defined the mass. Does that make sense? So this is understanding what those things mean. It's not just, oh, that's a number, okay, or it has that charge, but you're now applying, if I know that knowledge, what was the necessary thing that would follow from that? Okay, which would be great if I could explain deductive and inductive reasoning, which I still have a hard time with, and I've been sitting back in the class reading about it, trying to figure it out. I probably should have paid more attention to Craig's lecture. Okay? But we're using one of those forms of reasoning to translate that. I'm gonna guess deductive.
Are you gonna make us do all of that in the test, like you're gonna put the table and you have to define?
No.
everything? No?
Because I think filling in that table is just rote memorization. That's not useful. But I could say you have 6 protons. What could you tell me?
Ask a question.
Okay, as a question. Now you can apply a lot of that information out. Okay, so we end up using those meanings to come up with different terms throughout the semester, throughout the content. Does that make sense?
Yep.
Okay, so I said 6 neutrons on carbon, right? Could I have said 7 neutrons?
No,
That's a different what?
that's
Right, that would depend what number. Okay, what are you talking about? Okay, so voice what you were going through.
we're making a different element.
Different element. Okay, if I said 7 neutrons and 6 protons, you're saying different element. But the neutrons don't define the element. What do the neutrons define? The mass. So it's not a different element. It would be a different isotope. It would have a different mass. If we have elements with multiple different neutrons, those are now referred to as isotopes. Okay? So we invent a term. So I would argue that defining the mass, while true, is a little bit vague and not quite as useful. This is better labeled as defining the isotope. Okay? So I could look at a case of carbon-12. And what would that mean? I have 6 neutrons. I know it's carbon, so it has 6 protons. That number that's coming at the end is the mass number, so that means I must have 6 neutrons. If I said carbon 13, I have 7 neutrons. Okay, it turns out that there's multiple possible isotopes for carbon. Carbon-12 and carbon-13 are super common ones. Super common is a bit of a weird statement, but let's just say that. Okay? They're common. If I now want to report the mass of carbon, well, what would the mass of carbon be? If it's 12, does that take into consideration the mass of carbon-13? No. 20. Where'd you get 20 from? Okay, that's fine.
19 is 3 plus 6 protons. Protons plus the 1.
How many protons do we have if we're carbon?
6.
How many neutrons do we have if we're carbon-13?
7.
7. That 13 is the mass. So if we say the atomic mass of carbon is 12, are we taking into consideration the presence of carbon-13? No, because the mass of carbon-13 is 13. So what is the mass for carbon? Right? What does it depend on?
The isotope, if it's an isotope or not.
But I'm not asking for a specific isotope. I'm not saying what is the mass on carbon-12 or the mass on carbon-13. I'm saying the mass for all carbon.
Depends on the neutrons.
That's on a specific atom. And this, I know this is challenging. That's why I'm pushing on this.
Is that the atomic weight now?
This is where atomic mass comes in. Atomic mass takes into consideration all of the possible isotopes. Right? Our atomic mass is the average mass of all of our isotopes. So if we look at carbon with those 2 isotopes, carbon-12 and carbon-13, what do you think our atomic mass should be? 12.5. Why 12.5?
It's the average.
It's the average of those 2 masses. Phenomenal. That's what atomic mass is. It's the average of the mass of all of our isotopes. Yeah?
You have to calculate that on the test.
Yes. Okay.
Oh, that.
But let's make this a bit worse, because so far it isn't all that bad. Believe it or not. Okay, so we had someone shout out, well, it's 12.5. Well, let's get to the 12.5. How did we do that? We have 2 isotopes. What's the average of 2 things? What do I have to do? I add them up. and I divide by 2. That's how we take an average. We add all of the individual values and we divide by the total number in that sample. Yeah? So if we did that, 12 plus 13 is 25. It's okay. Divided by 2, 12.5. So for those people that were able to do that calculation that rapidly in their head, fantastic. You don't need to. You've got a calculator. You can enter it into the calculator. There's your work, 12.5. That would be the atomic mass for carbon. Okay?
But it says 12.1.
But Mike, it's not 12.5. When we look at the atomic mass for carbon on the periodic table, what does it say it is? 12.01. So what is wrong with the calculation I ran here?
It doesn't get more than 2 isotopes.
It could be that there's more than 2 isotopes. There's a larger issue, actually, when it comes to the isotopes.
Is there way more carbon 12 than 13?
It's the amount of each of those individual pieces. When we ran this average, this was just a normal average. Okay? This assumed we have equal percentages of carbon 12 and carbon 13. That information is embedded in the formula that you guys memorized. Okay?
On the test, will we be told if it's not equal?
Yes. We'll look at an example here in a second. So I got to do this one. So I'm going to shift that calculation upwards a little bit. So we said 12 plus 13 over 2, right? Okay. We're going to do some mathematical manipulations. Okay. Or as my dad, as a mathematical or a math major, would say, some mathematical masturbations. That's just what he did. That's what he said. 12 plus 2, or 12 over 2 plus 13 over 2. Am I allowed to do that? Yeah. This is 1 over 2 times 12 plus 1 over 2 times 13, yeah? Yeah. I want to take into consideration percents. How much of each of those isotopes are there? Percent. What does percent mean?
How many hundreds?
Per is a division, cent being 100. So I need that division, that 2 needs to become 100. It has to be per 100. But I can't change the meaning of that being 1 over 2. So what has to go in the numerator? 50. And we'd better get the same answer, because if we don't, we screwed something up. Okay? But why go through and manipulate this? And you're like, I don't know. This is 50 per 100, known as 50%. Okay? So what we've just gone through and done is shown that with our standard formula for calculating averages, we've assumed an equal percentage of each. If there's only 2 isotopes, the equal percentage is 50%. So if we genericize this, the percent of one isotope times the mass of that isotope plus the percent of the next isotope times the mass of that isotope, should equal the atomic mass. We're like, oh my God, that's crazy. That is literally the exact same thing as we did up here.
Yeah.
There is no difference between it. It's just a question of, have we pulled that information out so that we can critically evaluate it? Okay? Where this becomes incredibly important, that average that we ran up here, 12 plus 13 over 2, what that is what's known as, and I'm probably going to mess this up, but I think it's true, an algorithm. What? No, that close enough. Thank you. It's an algorithm. Okay? What does that mean? An algorithm is something that we create so that we can repeat a calculation hundreds of thousands of times without having to think about it. We've uber simplified it. Algorithms are fantastic for computers. If you go into a class and you learn algorithms, what you have learned is how to not get a job or how to not keep a job. Because all you've learned how to do is do something that somebody can program a computer to do. You've learned something that we could literally teach a 5-year-old to do. What you need to understand is not the algorithm, but the larger process. And before you start going through and saying, well, I have to know that formula, and repeating that formula is now an algorithm. Yes, that is an algorithm, okay? But that algorithm process allows me to apply to a much broader situation, and I'm going to butcher the hell out of this one. Heuristic?
Yeah, that's right.
Did I actually spell that right?
I think so.
Oh, cool. A heuristic is now how do I solve a question at a much broader scale. Okay? If we look at the jobs that Intel offers, you get operators. Operators go through and do the bulk or majority of the processing behind the work of building things. Okay? When something fails, operators cease to function because they don't know why it works. They know what they need to do to just make it work. That's when you bring in an engineer. The engineer comes in and says, okay, this is how it was supposed to work. Based off of all this information you're giving me as the operator, I can now process what went wrong, fix it so that I can make the operator go and do it again. The operator gets paid a fraction of what the engineer gets paid. Okay? Where my wife works, it's like a factor of 10 difference. Okay? Because the operator doesn't need to know how or why it works, they just need to do the action of running it through. That action takes valuable processing time away from the engineer. And the engineer could spend their time better learning how and why the outputs are the way they are. Okay? So what I want you to get out of this class is not algorithms to solve. Okay? Because you can find those anywhere. What I want you to think about is what are the heuristics? What is the larger scale thing that allows you to apply out to more problems? That becomes very challenging to deal with. Because now you have to go, oh my God, what's the bigger picture? That bigger picture takes a lot more time and effort behind. When it comes to an exam, do you really want to be spending all of your time on heuristics? What do you want to be doing on the exam? Algorithms, so you can get through it faster. Okay? To get the algorithm to a point that's useful, you have to understand the heuristic so that you can build that algorithm quickly in the exam. Kind of, sort of. At this level, that is challenging. Okay? This is why you should be practicing things to get used to those patterns so that you can apply them more efficiently when it comes to an exam. That's the point of practice.
Will you show us an example of when a percentage is not 50-50?
Yep. We'll actually pull that up in just a couple seconds. I'm actually like 2 or 3 slides ahead of where this is supposed to come in.
So does this lead to like calculating abundance for isotope?
So those percents, percent A, percent B, those are abundances. When we calculated our normal average, our algorithm process at the top, we assumed 50%. Was that 50% inherently obvious in our algorithm? No. What did we have to do?
Assume.
We had to have that assumption. How many of you actually knew that assumption was there and embedded in the calculation? All we had to do was break down that math and effectively reverse engineer our assumption. It's embedded in the calculation already. We just didn't know it. What if we had 3 different isotopes? Well, this would be 1 over 3. You flip that all the way down, it comes in at 33%. Okay? The algorithm takes into consideration and just says they're all equivalent. This equation, our heuristic here, works when? In all cases. The algorithm works only when they're all the same. Okay? Yes?
Algorithm is without the second
Okay.
You can add it to the E in heuristic, the second.
Like that? Okay, cool.
Wait, so then what would it make if one isotope is more abundant?
Right? And so we'll look at a specific example of this in just a second. Right? So minimally at this case, what we can go through and say is that for carbon, they aren't equally abundant. Right? We know they're not equally abundant because if they were equally abundant, our answer would have been 12.5. What does the periodic table say? 12.01. Based off of that information, what can you tell me about carbon 12 and carbon 13? Not Anthony, because you did a good job answering those. What can you tell me about the abundance of carbon 12 and carbon 13?
One of them is much more abundant than the other.
One of them is much more abundant than the other. Awesome statement. Now you can't answer. Which one is more abundant? Carbon 12 is more abundant. We know carbon 12 is more abundant because when we look at the average, that average on our periodic table, 12.01, is closer to 12 than it is 13. So we know 12 must be more abundant than 13. Kind of, sort of? Kind of neat. We can pull a lot of information by just knowing those relative positions. Can we run exact calculations? Which both Ali and Tasha were asking about. Not yet, but we'll look at that.
So, I'm a little confused. If there was like, is there always gonna be like 2 or like what's
No.
the highest it can go up to? Are you just like gonna keep going?
So what I would recommend there on deciding how many isotopes there are, Wikipedia. Pull open the Wikipedia page on isotopes and they'll show you what are the common isotopes and how they align out. There are, I think it's 20 elements, because somebody wrote it down in a reading assignment somewhere that there's 20, because the textbook I think said it, 20 elements that don't have or have only one stable isotope. The rest of them have multiple isotopes. So like carbon 12 and carbon 13. Okay? When it comes to an exam question, you will be given that information, and we'll see that in a second.
If carbon 12 is more abundant, why doesn't it have more percentage on the atomic mass then?
It does. Remember, what is this calculation? This calculation was just to show the implicit. When we implied, we assumed 50.
But the big
And
one-
50-50 is wrong
alright.
because according to our periodic table, it's not 50-50.
Alright.
Okay? So, whoops, go ahead.
If the answer is already on the periodic table, why would
The-
you need to?
Answer isn't necessarily on the periodic table. So we've got to be a little bit careful with that. Okay? When you're saying the answer is on the periodic table, what was the question?
Well, asking what the atomic mass is.
Okay? So to that question, yes, it's on the periodic table. Which one's more abundant, carbon 12 or carbon 13? Is that actually on the periodic table, or are you doing an interpretation based off of what we just talked about?
Interpretation.
You're interpreting, okay? Does that make sense? So depending on the question, it's not explicitly on the periodic table. The atomic mass is explicitly there, and that's what you will largely use. Okay? So let's take a look at another example. This is our isotopes. We can define our isotopes. For hydrogen, there's 2 common isotopes. You'll notice we don't call this hydrogen 1 and hydrogen 2. We call it protium and deuterium. Why? And for people wanting to write down those names, don't stress about the names. Okay. We studied the isotopes of hydrogen so much that we gave them names. They've just been studied for that long that we gave them their own name. That's it. That's all it is. Why did we give them those names? What is the hydrogen 1 isotope made of? Zero neutrons. How do you know it is 0 neutrons?
Because it's 1 minus 1 is 0.
Okay? So we can do a couple things. 1 minus 1 is 0. Our atomic number was what?
1.
True. What did it mean?
1 proton.
Number of protons. Our mass number was what? Don't tell me 1. What did it mean? Where did it come from?
Protons plus
The number of protons plus the number of neutrons. Interestingly enough, if I want to get the number of neutrons, what do I have to do?
the mass.
I subtract those, and what do I get? 0. There are 0 neutrons. So what is in the nucleus of hydrogen 1? A single proton. Just one. What might I call it?
That makes sense.
The name that I've associated with it is protium, because what is the nucleus? It's just one proton. That's the only thing that's present. That's why I'll call it protium. Okay? All right, so what happens to the next one? It has 1 neutron. So this one, I named it based off of the pieces that were in it, right? It had 1 proton, so I called it protium. Here, what's in my nucleus? 1 neutron and 1 proton, so I could call it protnudium. That's kind of dumb. Actually, I think that's kind of a cool name, but we didn't call it that. We called it deuterium. Deuce. There's 2 particles in the nucleus, so it is deuterium. Turns out there's another isotope for hydrogen, where we've added yet another neutron. How many particles would be in your nucleus? 3. What do you think our name for that is? Tritium. Okay. So it's the same kind of aspect. Kind of makes sense? Okay, so when we're looking at our isotopes, we can reference them with their unique names, okay, if we wanted. We typically don't do that. Okay, why not? Only 20 elements were single elements. Every other one had at least 1 isotope. Okay? So if we invented a name for each one of those isotopes, we don't have 118 anymore. 236-ish. Right? We double them. Okay? But 20 didn't have isotopes. Some of them have lots of isotopes, like 5 or 6. Okay, so if we double, we're probably okay. That's a lot of work, a lot of effort. So what we've done is said for the majority, or for the most part, changing that 1 neutron, or 2 neutrons, or 3 neutrons, doesn't change the properties enough for me to change the name. Okay. Said another way, if I gained 20 pounds, would I still be called Mike? Yeah. Okay. Would I interact with the world a little bit differently? Yes. But am I still the same person? Yes. Does that make sense? 20 pounds really isn't that different when you're 6'4", dude. Just for the record. Okay? So we don't have to stress about those names, but I just want to give you that kind of origin behind that. Okay? So we could go through and look at abundances on that. So let's try that as just a first ballpark. Which of those isotopes do you think is more common? Protium or deuterium?
Deuterium.
Okay. How would we figure it out? What's the atomic mass? So we go to the periodic table that tells us our atomic mass. And the periodic table tells us our atomic mass is 1.01. So it is approximately 1. Which of those isotopes is closest to 1? Protium, which means protium's the more abundant. We can use that information on there. How much more abundant? How close is it to 1? Really close, which means it's almost completely protium. It is. It's about 98% protium and 2% deuterium. Okay, you don't need to know those numbers. Don't stress. Okay, but we're able to approximate and come up with those relationships because we understand something about where those calculations are coming from. Kind of, sort of? Did you guys just look it up? It depends. Some periodic tables will show that information. It usually gets way too cluttered. Except you can't use that one on the test. But why not? No, you do not have to memorize any isotopes.
You're going to provide us the periodic table?
Mm-hmm.
So we can use the ones that we have?
No, you can't use those.
Darn it.
So let's take a simple calculation first. How many protons and neutrons does an atom of lead-206 have? What do we have to be able to interpret when we look at that question? Cool. 206 is our mass number. The mass number is what? Don't tell me 206. Give me the other information.
Protons plus
Our protons plus our neutrons. Okay? What else would I need to know?
The atomic number. We either need to know the
It's not
atomic
that you're
number-
wrong.
We either
That's-
need to know the atomic number of the symbol, so that way we can figure out how many
Yeah.
neutrons.
Okay, and it's not that you're wrong, it's how I'm trying to logic through the steps that you're moving through to get there. If I want to know the number of, oh, it actually says protons and neutrons. Okay? If I want to know the number of neutrons, what would I need to know? I have to know the number of protons. So we can start off and say that's our mass number, that's the protons plus neutrons. To get the neutrons, I have to know the number of protons. To get the number of protons, what would I need?
The symbol or the mass number,
Not the mass number,
or the atomic number.
the atomic number. Is the atomic number given in the question? No, which means to get the atomic number, what do I need? I need the symbol. Is the symbol given in the question? No, which means
Memory. Or
I need to know, and I know where you guys are going with memorize. That's the next step, actually. To go symbol, what do I need to know? What has to be given in the question if it's not the symbol?
the name.
The name of the element I'm looking at. Is the name given in the question?
Yes.
Yes. So to answer this question, this is one of the things that makes chemistry challenging. This was a relatively straightforward question. We go, oh, it's just this, and they come up with a number. These were all of the steps that you had to do to answer this question. If you didn't know any one of those steps, what happens?
It's all.
It's all wrong. Okay? So when we talk about you need to know that protons define the element, okay? That atomic number is this. Each of those are language steps within this process. That's why we need to know the simple facts. It's not the simple facts you get tested on. It's the application to those facts through this process. Does that make sense? One question, and you had to do 1, 2, 3, 4, 5, 6 interpretations. Okay? And that's a straightforward question. Okay? This is why you need to practice, and this is why when it's the simple stuff, like, oh yeah, just atomic number is that, is an important piece of information that you need to start working on making sure you've got down locked, so that you can shortcut some of this. You already started to. You said, well, I need atomic number, I need to go to the periodic table. No, you don't. I need to know the symbol. I need to know the name. I need to know that that's specified there. Taking the information from the question and being able to transmute that into the steps that you have to go through and take, that's the important part, and that's the challenge. Okay? Try to not shortcut those steps on your homework. On an exam, shortcut the hell out of them, but at your own risk. Okay? Because if you start shortcutting, you may solve for the wrong question. Okay? So, there's at least one hand. What do you got?
Alright, so it's led 206. Can I go and look at the atomic weight and then from there know which it's, if I didn't remember?
What is the atomic weight?
Oh, never mind. I was gonna
Oh, sorry, you can't never mind it. I asked the question this time.
um,
You can never mind your question. You can't never mind mine.
alright.
What is the atomic weight?
It's the,
82.
The atomic weight is something you have to solve for. Okay? That was a calculation. That is the average of all of the isotopes. Are we looking at all of the isotopes in this question? No. So the atomic weight is useless information. I don't care about it.
so I can look at it together closely to which it is.
So you could look at it, and what is that going to tell you?
Well, this
it's
is
207.
Yeah.
So it's closer to 207 than it is to 206. Does that change the question? It has no bearing whatsoever to the question. I know where you're going. How can you change the question? That's okay. Make sure you answer the question that's asked.
Okay, but my question was more like, can I look at it to
know, like which one it, because like, for example, I didn't remember which one was the symbol for lead, so can I go on the atomic number and it got me close to PV?
I see what you're saying. Are there ways that you could reason through other pieces of information? That is possible, okay? You're saying you don't know which one's lead, so you're going to use the mass number, which should be pretty close to the atomic weight. So we could go through and look. 204, 207, 208. It's probably one of those, right? You may just decide it's PB because that's the closest, because it's off by 1, where that one's off by 1.5.
Yeah.
That could be a bit sketchy. But if you got nothing else, yes, draw from whatever you got.
From there.
Yeah.
I don't remember. All right.
Yep.
Try to remember.
Yeah, you should try to remember as much as you can. But definitely pull from whatever tools you've got. In that point, if you get to this and you're like, I don't remember what symbol lead is, should you be going down the path of which one's closest?
Yes.
No. You should skip the question. You were already going to get it wrong. Skip the question, move on. Okay? It's not don't embarrass yourself. Okay? It's skip the question, move on. Go through the rest of the test. Now that you've answered all the questions that you know were right, now you can double back and be like, well, let's just kind of guess my way through. If you start guessing your way through, you're now spending time on a question you already don't know. The very next question you could know the answer to, if you don't get to it, you haven't proven that you know that. Does that make sense?
Okay.
So at any point where you're like, I think I could reason through this, that's okay. You could write a quick note, reason through this way, and then move on. Don't spend more time on it. It's already a question you're more prone to get wrong. Okay? Yes?
I have a question about the RSW, or RWS numbers, about one of the songs. About the atomic mass.
Atomic mass. We'll actually look at that next.
Okay.
This was to do it simple, and now we'll make it more difficult. Okay? So our percents, something over our totals. Are we okay with percents? Like, do we need to dig into that? Okay. If you want help with that, I'm fine to do with that. What we've gone through and done is some more specific targeted examples. We can look at general ones outside of class if you would like. Simple versus weighted averages. Okay? So what you guys have really been asking for is this question. Okay, so go ahead and read that question while I write up the formula, okay, that we've been using, okay, which you're fine to memorize if you want. You guys have it? If you think you know where to go ahead and start working on solving it.
Oh, we need to work on it.
You don't have to. We're going to work on it here in a second. All right, so what we've got written across the top is our formula. You'll notice I added a percent %C. When we're looking at a weighted average, how many things could contribute to the weighted average?
However many there are.
However many there are. It could be 2, it could be 3, it could be 1 billion. The formula doesn't change. That's what's nice about that. A heuristic allows you to apply that out to everything, not one case. Okay? So let's go through and take a look at this one. Gallium has 2 isotopes. Stop! What does that mean?
You just got 2 parts of it.
There's only 2 parts going into it, so based off of the formula that I've got written up top, I can already make some adjustments. What could I do? I can take out C and that plus, and I'm going to stop scrunching mass over there. Right? Cool. Now we got the rest of the question. Gallium-69 with a mass 68.926 AMUs. Let's pause for a second. That was 69 and 68.9. Those numbers are getting all over the place, right? That could be easy to lose track of. It might be nice to simplify this. Instead of saying gallium-69, I could say mass of 69 isn't necessarily a problem, okay? But what is the mass of 69? 68.926. Not 69. And it could be easy to confuse those numbers. So I want to try and get away from using a number as a symbol. Gallium-69 is a symbol, not a number. Everybody recognize that? Okay. For those of you that did the measurement lab, we did the measurement lab, right? Okay. This might be a good thing to take a look at. Okay. On the back, it said, convert the mass of the 125 milliliter Erlenmeyer flask to centigrams, or whatever it was. Okay. I got a bunch of people saying 125 milliliters to grams. I don't know how to do that. That's because 125 milliliters is not what it asked for. 125 milliliters was what?
The volume.
The name of the flask, which happened to be its volume. But that 125 milliliters, you see a number, you're like, oh, I got to use it. No, that 125 milliliters is literally a name. Okay? It wasn't a mass.
It was us.
Okay? It's just the name of the container. Using numbers as names and as measurements can be very confusing. So try to simplify it. Instead of saying gallium-69, I could call that A.
Oh, okay.
Okay? Why would I pick A? It's the first thing in the list of the formula that I memorized. It's now easier. Okay? I could even color code this because I've got colors. This 68.926 applies to what? Yes, it's the mass of what? A. That's my red value. That's going to A. 60.11% abundance applies to what?
The percentage of A.
The percentage of A. This is where language becomes confusing when we read through. A with a mass of this, 60.11% abundance, and gallium-71. Those two numbers are tied to the first thing that appeared in front of it, A. The and is what differentiated those. This is A. Gallium-71, there's a freaking number again. A number is a name. I don't want that number as a name. So I'm going to call that B. Okay? So we could now go through and try and take that information and fold that into my equation above. Do I know the percent of A? Yes. Okay, it is 60.11% per 100. Okay? For those of you that want to say, well, isn't that just 0.6011? Yes. How did you do that? You divided by 100. You just did it in your head. That's the calculation that you did to get that. Okay? Do we know the mass of A? What was it?
16.926.
Okay? Do I know the percent of B?
Yes.
Where does it say the percent of B?
You only have two, so it has to be the remainder of.
I have two isotopes. It does not explicitly state the percent of B. But what it does say is that I have two isotopes. So if I take the percent of A plus the percent of B, what should I get? 100%. I therefore know that the percent of B is going to be 100 minus the 60.11. 39.89?
Yeah.
49.
I think it's 39.
39.8.
Yeah,
Okay. That was a percent, so 39.89 per 100. Mass of B. Am I given the mass of B?
That's what you're searching for.
Not only is it a no, I'm not given the mass of B, but more importantly, that's literally what I'm solving for. How do I want to write that into my equation? What's that?
An X, like a variable.
So we could do it as an X. That's fine, a variable. What else could we do it as? B. Doesn't matter. You're putting in a variable to represent what that term is. Yeah?
Yeah.
Okay. This then has to equal what?
69.7.
Not you.
Yeah. Okay. I won't take it personal.
You shouldn't. It was good. What does that have to equal? Two answers. One answer I want more importantly than the number. What does that have to equal?
The atomic mass.
The atomic mass. That's literally what the formula is. Does it say the atomic mass?
No.
Damn it. But since you are a smart pioneering chemist, you recognize that you will always have a periodic table, and the periodic table will always have the atomic mass written on it. So now, because it didn't even write out, it actually gave me the symbol. I know the symbol is Ga. I can go to the periodic table, find Ga right here, and pull down the atomic mass. The atomic mass of 31. No. What's the 31? The atomic number. The atomic mass would be 69.72. Right? Now I can solve for x. How are we feeling? Okay. Some people are okay with it, some people aren't. That's okay. That's why we practice. But this is the process of moving through it that you should be using.
Are we gonna do another one right now?
We're not going to do another one here. No. Go ahead.
Can't you just use the atomic mass and subtract the mass of A to get the mass of B?
What would you get? 69.72 minus 68.926. What do you get? I'm not good at math. 1.12, whatever. We get 1.132. Does it make sense that the mass of a gallium atom would be 1 anything? Why not? It's too small. The gallium atom, according to the atomic number, has 31 protons, which means it has to be at least a 31 mass. Just subtracting them doesn't work. So you can't just subtract. And this becomes one of the challenges. It's like, well, I don't know what to do with these. I'm just going to start doing some mathematical operations. You can't do that, okay, for a couple reasons. One, I'm going to be thinking that exact same thing, which means when I write the multiple choice answers, guess what one of the answers is? The 1.132, which it wasn't that number, right? But I'm going to do that. Why?
Because you're a mean.
Because I'm aware that there are ways to make common mistakes within the calculation. I'm going to put that number in there to see if all you're doing is just jamming numbers together and hope it spits out an answer. So just because you see an answer in the multiple choice does not mean you did it correct. What it means is you either did it correct or you did it the way that I know you're going to do it wrong. Okay? If we look at odds, I think you're going to do it wrong 4 ways. I think you're going to do it right 1 way. Just mashing numbers together, odds are you're going to find one of the wrong ways, not the right way. You have to understand the process for how to get the correct answer, not just jam numbers together. Okay? This required a sizable amount of work, right? So if I put this in a multiple choice question, you could get this one wrong and lose all of the points. That would kind of suck. Okay? Maybe you did a simple calculator mistake, couldn't get a number that matched any of the answers, so you just guessed and you guessed wrong. That's why we have show your work. You would show me this work. And guess what? You get the wrong answer at the end of it, it's 5 points, you get 4 out of 5, because your work is spot on, perfect, it's exactly what I want to see. You just haven't learned how to enter the calculator correctly. That means more practice, maybe less stress during the exam. How do you get that less stress during the exam? By doing more practice outside of the exam. Okay? Yes?
Are you gonna ask us for all of the percentage, like the part of the bottom, or can I just put the formula, like if I already got the number?
Was this 39.89 explicitly stated in the question?
No.
No. Did you have to know some information to get that?
Yes.
Yes, then you have to show that.
You don't have to show that.
Yep.
All right.
You may be like, that's trivial. You kind of have an argument there. I need to see it.
Okay.
Minimally show me 100, B is 100 minus 60.11.
Okay.
Okay? And I can pick up some of that context. Ideally, everything up here would be shown.
Sorry, we get back. Can you solve for x again? Because I'm still confused.
So I didn't actually solve for x. Okay? So we can do that right now. But to do that, I have to delete some stuff. Can I delete some stuff?
Yeah.
Okay. So I'm going to delete everything below that line. Okay. And I also need a calculator because I cannot do that math in my head.
Yeah,
Okay.
so something.
don't you give me the answer.
So how did you get 69.72 without solving it?
What was 69.72? The atomic mass. Where's the atomic mass? On the periodic table. I did not solve for X yet. Atomic mass is something that's found on the periodic table. PT for periodic table. So to start off with, 0.6011 times 68.926. We're just doing that first term. 41.38.
4314. I don't know how much numbers do you want.
Give me one more.
4.
Okay. For the next one, I can do that one by myself. 0.3989 times x. This equals 69.72. I'm going to subtract 41.43. I'm pretty sure I'm butchering that number. 314. Do that subtraction for me, please. 28.29. Give me a couple numbers. Oh, it came out exactly that. Okay, never mind.
Oh, I got some.
What did you get?
28.285.
285. It's probably the different string of numbers.
Oh yeah, how much numbers do you want in the calculations?
We can address that in a second. Divide both sides by 0.3989. So take your 28 point change and divide it by 39.89 or 0.3989.
70.92.
Say that again.
70.92.
Flat.
Whatever.
0.03000.
0.003, so you want to.
Okay. So something along those lines. Okay. Depending on how many numbers you strung through, you might see some variation within that, but that should be ballpark what you're getting.
Huh?
Okay.
Oh, yeah.
So this isn't chemistry.
That's not chemistry.
This is our algebra and math side of the class. We get English interpreting the question to get us to the work. Now that we have our work, now we can do the math. So most of chemistry isn't a chemistry class, it's an English and math class. So people are like, oh, it's weird that you would put English and chemistry together. No, it's not. That is literally what the class is interpreting how we represent language of science.
So if it's only 2 isotopes, shouldn't the number be close to the
Which one I'm going to address here in a second, but yes. Okay. So we come out with a number, x is 70.92. We've now solved for it. It said 4 significant figures. Okay. We can just do the first 4 and we're done. Okay. You won't see an answer of 70.920. Why? Because we haven't officially talked about significant figures in lecture yet, so don't stress. It's shown up in the video, but I'm not talking about significant figures in lecture. We aren't doing enough calculations to worry about it, so you don't have to worry about that yet. Okay? Can I erase some stuff again?
Yeah.
Okay, I want to leave that answer there. What's your question?
You said you record your lectures.
Yep.
Where do you find them?
On Canvas, if you go to modules, there's a module that says all lecture videos. The lecture videos get uploaded into that from YouTube. But if you go to the YouTube channel, they're in a playlist for this course. What is the mass of gallium-71? We got a mass being 70.92. Okay, let's take a look at gallium-69. What was its mass? Okay, 68.926. Is that close to gallium-69?
Yes.
What should our mass be?
Close to 71.
It should be close to 71, does it? Okay, so we have a reasonable check there. So yes, you can do that as a reasonable check. You could go through as a reasonable check and just check your multiple choice answers. If only one of them is close to 71, ta-da, there's your answer.
I mean, like, also the atomic mass, because it's like 0.72, wouldn't that be like 72%? Or am I
No, don't do that. Don't do that.
What is AFU?
AMU is an atomic mass unit that I am intentionally dodging and not trying to reference because it is ultimately one of the most useless mass units that we could be discussing. So you don't have to stress about what an AMU means. We'll address that a little bit in the third unit.
So, I got some questions. So on the test, you're not gonna put on the test as an option 70.920 because
True.
you're asking.
No
for-
sig fig things are going to show up on the
Okay.
test.
And are you gonna put like, for example, 70.92 and 70.92 AMO or something like that? Or-
No.
No?
Yeah.
Do we need to put the
I
AMO then?
shouldn't be doing that. Because what you'll see here is what is the mass in AMUs. The unit is implied within the question, so you wouldn't have to specify that. If it says 70.92 grams, you better not click that one because it literally says a different mass unit.
Okay.
Okay? That's a level of trickiness that sometimes they do. It's rare.
So with something like that where there's only one obvious answer, do we still need to be showing work to get the credit?
Do you
or-
need to show work if there's an obvious answer? There's two answers to that, yes and no. You do not need to show work at all if it's in your not shown work section. You can just bubble in the answer. If it's in the show your work section, if it's an obvious answer, it's in the show your work section. Show your work. That's why it's placed there. Okay? So what may have happened is I intentionally set it up with one obvious answer as a subtle hint to help guide you to work that allows you to get the correct answer. Okay? Which I do.
Wait, so on one of the RWSs, it said what's the symbol and then what's the name. So it was like potassium and what's the symbol.
Mm-hmm.
How would you show your work for that?
So what would you go through and do to say that? How do you know potassium is K?
I just do it. I memorize the periodic table.
Okay, so you could say you memorized the periodic table. Where was that information found? Do you have the name for W? RE. OS? RU. TC. Where's that information found? Okay. It's in the book. It's also online. You could say I found that online where it matched names to symbols. That's fine.
So writing where the information is.
Identifying where the information is. And this becomes another thing when it comes to homework. What is the point of homework? To learn it. Okay? By saying, well, the symbol is just potassium, it's just K because I knew it, that's not you showing that you learned it. Why are you writing that as an answer? What is the point of homework if that is your single response? What's the point?
To show that you did it.
If you just say potassium is K, what was the point of that homework? There is actually meaning behind doing that.
Just the memorization aspect of it.
He said he already knew it.
You said it earlier.
Reinforcing that knowledge?
Getting the points. Literally getting a point value for the homework. Okay? Is that what homework should be?
No.
No. Okay? So what you need to do is if you see something you're like, oh, that's obvious, that's okay. Go ahead and address how you can make it valuable for yourself. This is where all of the symbols and names are listed. So that when you go back to review for an exam, you can look at that question and be like, well, I didn't know what AG was. Where would that information be found? If you've done the homework, now you know. If all you said was potassium was K, you can't apply that knowledge. You've done an algorithm versus a heuristic. Kind of, sort of? Cool. Okay. Chapter 5, periodic table. Okay, we're going to whip through a whole bunch of stuff here because this is largely factual and we're way behind. So, periodic tables, there's a variety of ways you can organize a periodic table. That's the lesson learned on this image. All three of these are periodic tables. All of them are revealing different aspects about organizational structures. Okay? If we go through the history of it, we go way back. Dobreiner, don't worry about scientist's name. I'll tell you when you got to worry about a scientist's name. 1829, looked at all the elements we had, and he said there were patterns of 3. These 3 elements all react the same. These 3 all react the same. So we noticed triads. Why would he have pointed out triads? Father, Son, Holy Spirit. For those people being like, that's kind of ludicrous and crazy. Not 1820s. Okay? We're looking for patterns in life everywhere. We already have Christianity as a pattern. The patterns we find in the Bible are the patterns we're finding everywhere else. Why? Because it makes sense. Okay? Why only groups of 3? They hadn't discovered enough elements. If we continue to move through history, what are we, 30 years later? Newlands goes through and actually says the 62 elements, instead of going in threes, are better in groups of 7. Okay? He's also added atomic mass. So there's a second layer behind it. It's not just sets of 7, but now we see it organized by atomic mass. Okay? Why did he say sets of 7? Yeah. A, B, C, D, E, F, G, A, B, C, D, E, F, G. The law of octaves. Music. The patterns in music are now showing up in the patterns of science. Right? I think I did that right. Yeah. Okay. So there was a cycle. We noticed the patterns in music, so we could apply that. Oh, music. Okay, the art form of beauty and how things translate must be tied to the periodic table because we see these repeating patterns. Again, we're finding patterns and we're forcing those patterns on what we already have. Okay, really it comes down to Mendeleev. Mendeleev is the name you need to know. He becomes the father of the periodic table, okay, the current periodic table. We've got an example of it down there. He's still organizing by atomic mass, so it's not a real big leap from Newlands. But what makes his periodic table so much more special were these things called ekas. Okay, he's not saying that we have repeat elements showing up. What he's saying is that eka means that there's something there, and whatever that is, it's similar to what's near it. Okay, so that one's eka aluminum. That one's eka titanium. Okay? His periodic table is cool because what he went through and did is said, there's a hole here. All you experimental people that are going out and finding elements have screwed up. You haven't found one. It's right here. That's kind of neat. Okay? Then people go out and discover that. How kind of neat and interesting and cool is that? Let's take a look at some abilities. Eka-silicon, 1869 is when he predicts it. Germanium, the actual element for eka-silicon, discovered 20 years later. If I came up and told you in 20 years, your hair is going to be gray. Duh. Okay? Big deal. Okay? You're going to weigh this much. Okay? You might be, okay, that's starting to get a little more interesting. You have this % body fat. Okay? You're going to have a short temper. Okay? You will have 2 kids. Okay? You will be married. Okay? Your kids' body weight percentage will be this. You're going to be like, mother, you're just a crazy mother person. Okay? That's crap. Look at the predictions. 20 years later, gray. All of the metals are gray. Thank you. Okay? 72, 72.6. 55 to 5.5 to 5.32. Very high. We can't all be perfect. But 937, by all standards, is very high. Okay? Reacts with 2 oxygens. The density of that oxygen compound. Okay? These are insanely precise guesses. Okay? In 1869. You're a crazy idiot. There's no way that's true. 20 years later, oh crap, you are. Okay, we'll name the periodic table after. Okay? That's the power of his guesses. He's organized it so well that he can predict. That's the goal of science. We find patterns. Those patterns in and of themselves aren't useful unless you can predict them out to something else. Okay? This gets to the deductive versus inductive. He creates a theory and deduces what it should be. He's got his deductive reasoning. Okay? Kind of neat. Noble gases historically come in a little bit later. The noble gases take a little bit longer to come in because, number one, they're gases. Okay? How many people in this classroom are part of the nobility? Interesting. Nobody. Okay? Would we expect, like Prince Henry to sit down in this class? No, why not? It's part of the nobility. There's no way in hell he's going to slum with the rest of us, right? Okay? Same issue with the noble gases. That's why they get called the noble gases. Their reactivity is so minimal, they don't interact with things, so it's harder to actually isolate them. Okay? So those were discovered. We got a hold of those. We add a whole new row to the periodic table. Moseley in 1913 finally goes through and organizes with our understanding of atomic structure that nuclear charge is a better way to organize the periodic table than atomic mass.
Would we need to know like the group Roman numerals?
We haven't gotten there yet. Sort of, kind of. Periodic law, it's organized by atomic number, not by atomic mass. Okay, so that's a big conclusion, and that gets us pretty darn close to our official periodic table. There's lots of information stored in there, like the group numbers, okay? Those Roman numerals, the numbers above, okay? Remember, you get a periodic table. You get the periodic table on the wall and the one on your exam. Do you need to memorize the Roman numerals? Nope. Why not? They're on the periodic table already. You don't have to worry about memorizing that information. Okay? Some of those groups get particular names. Okay? So we have to know something about their names. So first off, it is a grid pattern. We have to reference our columns and our rows. A vertical column is known as a group or a family. Okay? You've probably seen that your family responds to different situations kind of similarly than other people's families. Like you all sit down for dinner, okay, or you all stand up for dinner, right? Different patterns, okay, within a family. So within a family, they all interact with the world similarly. Not the same, but similarly. Okay, so our families are useful to have identified. The horizontal row is what's known as a period or a series. Some particular families or groups get names. The alkali metals, alkaline earth, I'll just summarize them here. Okay. The pnictogens, the chalcogens, the halogens, and our noble gases. The ones that you should know would be those. Why the? Yep, you need to know those. You have to memorize those names with those particular families. Okay. Alkali metals, drop the term metal. How many words are there? 1. Which column is that in? First column. Alkaline earth, drop the metal. How many words are there? 2. Which column are those in? 2. That way you keep them straight. Okay? With that, we're still wickedly far behind, but we've caught up a little bit. We will pick up with this fun slide on Thursday.